you might not have a solution. When you even find the minimum, there may be many such x that give you that minimum, so you want to pick the smallest one in that case. All right, so we cut this into two parts, right? So we said, well, first we find the set Z, which consists of all solutions that minimize this expression. So we said we take a minimum of all x, the difference between ax minus b, 2 norm, then this should be equal to az minus b, 2 norm, right? So all potential solutions of x are taken, right? Then the final minimum norm solution will be from this set x. You want to find x such that, so x should be in Z, and if you look at the norm of x, of this x, equal to the minimum over all solutions of the 2 norm, okay? So the smallest is the 2 norm of that set, okay? That's what we want. It's like cumbersome to write it down. All right, so the way we do this is exactly like you're solving ax equal to b, except we can't write ax equal to b, but because we know that it's not going to be the case, we work inside the norm instead, okay? So we say, okay, suppose we're looking at ax minus b, right? So we have a matrix A, column x, column b, 2 norm, right? And we want to find all the vectors z that can go in the position of x first, right? So we want to find the x that makes that as small as possible. So we understand that if you take the LU factorization of A, you don't make much progress. All right? Also, calculus will struggle a little bit with this. So what we do instead is that we take the SVD of A, and we plug it in, then this is what we're looking at, right? So remember, the only unknown numbers here are x. All the numbers in A, all the numbers in B are known too. All right? So then we said that, well, if you're solving A, we'll take the U to the other side, but we can do that by just inserting a U transpose over there. And the reason why we can insert it now is because use orthogonal, and if you put a U transpose there, it doesn't change the length, right? So this number is still equal to this number with that U transpose inserted in there. So this then becomes minimizing sigma V transpose X minus U transpose B 2 naught. Right? We need to find an X that minimizes this equation instead, right? And for every X, these two numbers are always the same. No matter how I pick the X, those two numbers are always the same. All right. So we do just as before, just like if I was solving this equation. If I was solving this equation, right, I would first multiply on the left by U transpose. I'll get sigma V transpose X is equal to B. I would like to take the V to the other side, but it's trapped by the sigma, so I can't take it over. I can't take the sigma to the other side either because it's not invertible. So normally I would then define this as a new unknown Y, and I would proceed, right? As long as this change does not introduce new solutions or kill the old solutions, then I'm happy, right? So same thing over here too. I'm going to make a change of variable. I'm saying I'm going to look at all the numbers generated by this equation instead, okay? Norm of sigma Y minus U transpose B instead. Okay, so I'm going to skip from this set of numbers to this set of numbers, right? As I change X, for every X I get a 1 number from this expression. For every Y I get a number from this expression. I claim these two set of numbers are identical, right? And it's easy to see why, because for every Y I get a number like this, but for every Y, if I pick an X, such that V transpose X is equal to Y, or take the X to V to the other side like this, then I can get the same number back. Okay, so there's two identical set of numbers, so minimizing over identical set of numbers gives me the same minimum back. Okay, and if I know the minimum in one case in terms of X, I know the minimum in another case in terms of Y, and so on and so forth. I can go back and forth between the two minimums easily. Okay, so I lose nothing by this change of variables. Right? And this elaborate argument that I'm doing right now is something you should repeat every time you look at an optimization problem. Okay? Don't just change variables. Okay? There's no such thing. Right? Just like an integration too, right? When we change variables, you have to be careful. If you do it the wrong way, you'll get a different integral. All right? Right? So you make sure in integral you're adding up numbers. After changing, you must be adding up the same set of numbers. Or at least you must add up numbers that end up with the same answer. Right? I mean, you have to make that argument. All right, so let's go. So we're going to go to this problem now, right, or Y instead. And again, we have to isolate Y, but so we can't just move the sigma to the other side. We'll change the 2 norm if we do that. So we've got to look inside, okay? So just like how when we reach this part over here, we will break it up into, we will look inside it. Right, that's how you proceed in LU factorization too. So you've got to look inside once it's not invertible, right? And the matrix notation stops being useful. You've got to block the matrix and look inside. I mean, you could block it all the way to 1 by 1, but it may not be very useful. Okay, so same thing here too. We're going to block. So we know that sigma r is the invertible part of the SPD. So there are r numbers here, minus r numbers here, so on and so forth. So we block y the same way. So y1 and y2. Right? And then this is r numbers here, m minus r numbers here. So we block u transpose b the same way. And you can check it's u1 transpose b on the top and u2 transpose b at the bottom, right? Because in the SPD, when we write it down, we partition A like this. Okay, so A is equal to u sigma v transpose. We put the first r columns of u here, the second r columns over there, right? And then we have sigma r 0, 0, 0. And then we split v as v1 transpose v2 transpose like that. Okay, that's the splitting that we do. Everything is r. This is r and minus r like that. All right, so you should remember how the rank goes with these numbers. All right, that's very, very important, of course, right? You can't just randomly split it. Right, so the top part is u1 transpose b, right? Because u is sitting like that and u2 sitting like that. So those are the two numbers. Right, so now we can write not equal, of course, minus sign. So we can write down the two norm of this, right? So let's, for simplicity, just square everything so we don't have to carry a square root everywhere. Right, if I square this expression at the bottom, so first let's subtract it. If I subtract on the inside, I get sigma r y1 minus u1 transpose b, and at the bottom I get u2 transpose b. That is the block column vector I have to write down. Two norm squared, like that. Okay, we have to minimize this expression over all y's. So what? Did I miss something? Oh yes, that's a minus sign, sorry. Thanks. Okay, so this is what we have to minimize. Notice that we have to minimize this over all possible y's, but a portion of the y has disappeared now, right? Remember the bottom portion of y, the y2's only multiply these zeros, so they drop that. Okay, which is exactly sort of what happens with the free variable, right? They sort of multiply u1, 2, and we sort of say, well, it's like a 0, we take them to the right-hand side. Same thing over here. So of course, when you take the 2 norm of a column vector like this, you might as well take the 2 norm of the top part squared, right? It will be the same thing, and then the 2 norm of the bottom part squared. And of course, if you change the sign of a vector, you don't change its length, so I can just drop that part. Okay, that's the expression. And you notice that in this way of writing the expression, it's the sum of squares, one term does not depend upon the y at all. No matter how I pick y, which means no matter how I pick x, this number does not change, right? Because u2 comes from the matrix A, which is fixed, so u2 is fixed once you pick the SPD. B comes from the right-hand side, that's fixed, right? So this number does not depend upon y at all. So when you pick y, only this number changes. So when you're minimizing over y, the only number that you can change is this one. But you see that this one can actually be made 0, right? If you look inside the matrix, you see that sigma r is a square matrix. Sigma 1 to sigma r is r by r. Y1 is column of length r, and the right-hand side is u1 transpose b, right? The length r. But you can make this 0 by picking y1 to be sigma r inverse y1 transpose u1 transpose b, right? So you notice that this number can be bigger than 0. So if I can pick a y to make that number 0, then reach the absolute minimum, right? Because no matter what I pick for y, I cannot change this number, no matter what I do. So you just have to minimize this because this is a sum of two non-negative numbers. You just minimize the first one. But you can make the 0, right? So if I just pick y1 to be sigma r inverse u1 transpose b and plug it back in, you see that is 0. And you see that is unique, right? If I want to make this expression 0, right? That's the only time this norm is going to be 0. I have to solve the equation u1 transpose b is equal to 0. But sigma is invertible, so you end up with that. That's only one answer for this, right? This is unique. There's exactly one y1 that does it. All right. So we found all solutions y that minimize this expression. Why? Because y2 is completely free, right? Notice the y2 just dropped off over here. So y1 is cast in stone, and y2 is free. Right? So y1 is the basic variable in this setup, and y2 is the free variable. Okay, so we have no all y's now. So we have all y's. So all y's. Just like this, you put the y1 on the top, the y2 at the bottom, and the y1 on the top is fixed, and the y2 on the bottom is free, right? This is the free parameter. So if you just enumerate for every choice of y2, you produce one choice of y, right? Now we want to produce all the x's, but that is easy too, right? Because to recover the x from the y, just do v times y, so let's just do that. Okay, so recover the actual x's that minimize ax minus b. So write it down over here. All x's that minimize to norm of ax minus b are given by each such x should be equal to v times y, right? But y is partitioned, so we partition the v2. So we put v1, v2, y1, y2 like that, right? We have to pick the y's and minimize it. So therefore, the y1 is constrained now to be sigma r inverse u1 transpose b. y2 is free. Write it all out. You get v1 sigma r inverse u1 transpose b plus b2 times y2, and that's all the x's. Okay, and you notice that this form of x is this very funny expression. It looks like a particular solution plus a homogeneous. Okay, don't write this down because it's not true. Right? Of course, the particular solution actually doesn't solve ax equal to b. Okay, that's not guaranteed, but this is actually a solution of the homogeneous solution of ax equal to 0. Why? Because we know that v2 is the basis for the null space of A. We know A times v2 is 0, so therefore this indeed is from the homogeneous solution. Right? So it's that null space translated to the particular solution. Right? It would have been a particular solution if u2 transpose b had been 0, then this would actually be the particular solution. But in general, u2 transpose b is not 0. So it's not a particular solution, but it's of the same form again. Okay, so we're going to look at this expression a little bit more carefully. Okay, notice that it is the same thing as writing it like this. Okay, these two are the same, right? But this form is a little bit nice too, and this form is also nice, it's not bad, but they're the same things. Okay, so remember, so this is all the x's now, right? So this is what I would call my z. So this my z now is exactly the x's that minimize it. So it's of the form v1, v2, sigma r inverse u1 transpose b y2, right? This is all my z's. So these are all the least square solutions. So if this set is empty, then there are no free variables. There's only one solution in the set, and that's normally called the least square solution. And you can show that if A was a skinny matrix with full column rank, then y2 will be empty, right? And then you would just stop over here. This is also the minimum norm least square solution. Of course, in your undergraduate class, you computed this without SPD. You did it with a QR factorization, or what is called the Gram-Schmidt process. Okay, so I put all of this stuff in the exercise for you. So with SPD, you just sort of get all of them and more in one shot. So now we need to find among all these z's, we need to pick the one that has the smallest length, but that's easy to do. Right? So the second step is to find the minimum norm solution. So we need to compute the norm of z, okay, and then find the smallest one. Again, to avoid writing squares, I'll just square it. So we want to find the length of z squared, right? But the length of z squared is going to be the length of this times this, right? So we have v1, v2, sigma r inverse u1 transpose b y2 whole squared, right? But this is an orthogonal matrix. And we know orthogonal matrices don't change the length of the vector they're multiplying. Therefore, the length of this vector squared is the same as the length of this vector squared. I can just drop the v as sigma r inverse u1 transpose b y2 2 norm squared. Right? But we're computing 2 norm of column vectors. You just take squares of sum of squares of the top part, sum of squares of the bottom part. So this is the same thing as the length of the top part squared. Just notice the equality plus the length of the bottom part squared. Right? This is just a version of the Pythagorean theorem. Right? Because if I put a 0 over here, that column vector is perpendicular to 1 if I put 0 over there. So they're perpendicular to each other. So the Pythagorean theorem should hold. Of course, you can just multiply and check that you get this. Right? You can just do the x transpose x and you'll end up with this one too. That's fine. Okay. So sum of this plus sum of this. And we want to pick the smallest z. Right? Remember, the only way to change z is to change y2. All the other numbers that appear in this expression are fixed. Right? These come from the SPD of A, it's fixed. This comes from the SVD of A and B. It's fixed. So the only free variables we have are y2. So the only way you can get a different z is by changing this y2. And you're unconstrained on how you can pick y2. It's completely free, right? So to minimize, to find the smallest z, the only number we're allowed to change is y2. But when I change y2, only this number changes, not that number, right? And the smallest this number can be is 0. So if I can make a y2 that makes the number go to 0, then I'm done. But the two norm is defined to be 0. Only the inside column is 0. So the only way I can get to the 0 is to make this guy 0. So that's exactly one choice of y2, right? The only way I can change z is by changing y2. If you want the smallest z, there's only one choice of y2. So we're saying that the smallest z is unique. Okay, of course, it's not at all obvious, but it turns out that, yes, by calculation, we can show the smallest z is unique. So that is the minimum norm least square solution. So that is obtained by taking the z in which y2 is 0, right? So we end up with just, so if I put a y2 0 over here, I end up with this expression. V1 sigma R inverse U1 transpose B, like that. Okay, and we notice that in this way of writing the minimum norm least square solution, that there is a matrix multiplying the right-hand side B, right? And that matrix is called the pseudo-inverse of the matrix A. So this is also written as X minimum norm least square solution. It's called A dagger B. Okay, and you can also take this as a definition of the pseudo-inverse. However, it's a little bit dicey to do it this way because the SVD is not unique. It is not clear if this is unique or not. However, if you go back carefully and think about what we did, you should be able to convince yourself that actually this X minimum is actually unique, irrespective of how you pick the SVD, but it's not very apparent, okay? So there's two other ways in which you can define the pseudo-inverse. Again, we'll talk briefly about both these ways, okay, to make it clear that this definition of the pseudo-inverse has nothing to do with this part. Okay, but before I do that, I want to go back and look at this expression without all this sophistication over here, right? So we're just going to look at the engineering way, okay? And this engineering way is how it is mostly used in practice. I'm going to go through it now, okay? So this way is a better way to think about this process. So suppose I'm trying to solve the equation AX equal to B, okay? So I'm going to carry this question mark with me this time. All right, saying, okay, maybe there's no solution. I'm going to wing it if there is no solution, okay? And if there are too many solutions on this side X, I'm going to do some damage too. So you say, well, okay, I'm not going to use the LU factorization. I'm going to use the SVD instead, okay? So I plug in the singularity decomposition. Well, I want to take as many of these matrices to the left, right-hand side as I want. So I first multiply by U transpose. I get sigma V transpose X is equal to U transpose B. Right? It looks exactly like the argument I just gave, but a little bit simpler because I don't have any two norms or anything surrounding it. Then I say, well, I'm stuck at this point. I call this variable y. Okay? But this time I will not even use y. Okay? I'm just going to partition everything. Sigma r 0, 0. Right? I got to look inside since I can't move sigma to that side. I partition v conformally, and I partition the right-hand side conformally too. Right? So this is the expression that I have to look at. Right, so no norm, no nothing, is just, oh, that's the equation I have to solve. I'm just going to use the SVD rather than the LU factorization. I'm just going to go for it, okay? I reach till here. When I reach here, then I have to multiply everything out. On the left-hand side, if you multiply everything out, the first equation reads sigma r v1 transpose x. And the second equation just reads 0 at the bottom. At the top, you have u1 transpose b, and at the bottom, you have u2 transpose b. Okay, that's what the equation reads. Okay, you see exactly the same expressions that we got, but now appearing much more readily, okay, that all the intermediate arguments. So you see that the second equation is, if there are any rows at all over here, you're basically in trouble, right? Because it does not depend upon, this 0 does not change no matter how you pick x, and the number on the right-hand side is fixed. So these are the constraint equations that we got in Gaussian elimination, right? So there's nothing we can do about this equation. We just eat it, okay? You cannot make the difference between the left-hand side and the right-hand side any better, no matter how you fiddle with x. So we just ignore this, right? So these are our modeling errors. We made some mistakes somewhere earlier, and a linear model has failed us, but we are probably expecting that anyway, since nothing's linear in real life. Right? So we just eat it. So we just ignore whatever it is. Right? You can tell the error is the size of this number on the right-hand side. This is the least square residue, as we would call it. Okay, we just ignore it. And we come to the equation on the top. And we see for the equation on the top, this is just odd numbers. So I can take this to the other side and I get V1 transpose X must be equal to sigma R inverse U1 transpose V. Right, so far so good. But the problem is that if you think about it this way, then how do we recover X? Right, because I can't take V1 to the other side, right? There's no way to take this guy to the other side. V1 transpose is a fat matrix. It's got the right inverse, but definitely no left inverse. Right? So what should we do? So let's think about this. So this leads us to this geometrical problem that occurs very, very often. And in many classes, they will actually go to this geometry. So in this class, I'm not so fond of this approach, but many engineers, especially in signal processing and communication and information, they talk about it this way. So we'll say something about it. Okay, so let's think about it. So I have this matrix V, which I split into two parts. Right? This is an orthogonal matrix. So the columns here are perpendicular to each other and also perpendicular to the columns over there. So my mental view of this world is that there is a hyperplane where the columns of V1 lie. Right? So that's the range space of V1. The columns of V2, all of them are perpendicular to this space. Right? So there's some space that is perpendicular to this. Okay, let's draw it like that. Some space that's perpendicular to this one that contains all the columns of V2. So the range space of V2 is completely perpendicular to this, right? In 3 dimensions, my only choice is 2 plus 1 splitting. Of course, in 4 dimensions, I can split 2 and 2 or 3 and 1. If I go to 5, I can do 1 and 4, 2 and 3, like that. Okay, I can split. So these are called orthogonal complements of each other. Okay, I didn't use the notation, but it is there. Okay, it just means I partition a full matrix into 2 pieces like that. When you say orthogonal complements, that's what, or if you talk about complementary subspaces, that's what you're saying. You took an invertible square invertible matrix and split the columns into 2 parts. This span one subspace, this span one subspace, and these 2 subspaces intersect only at the origin. Okay, they're called direct sums in that case. So since we are already in matrix notation, all those abstract definitions don't play such a big role. But when you go to infinite dimensional spaces where you cannot write matrices down, then those abstract definitions will, of course, take the place of these partitions instead. Okay, so you should look at the notes, but actually go through and make the definitions true. Okay, but anyway, so that's how it is split, right? So we're looking for this column X now, right? That's what we want to find. Ax equal to B, and that's X that we're looking at. Okay, what we do have about X is this V1 transpose X. Okay, we know what V1 transpose X is. What I want is X, right? So my question is, what is V1 transpose X? And is there a geometrical picture of this guy? Okay, and this geometrical picture is used extensively by engineers, so I should say something about it. Right? So let's see what is that. So what is V1 transpose X, right? So well, we don't know what this is, but let's not look at this guy. Let's look at V transpose X instead. Right? If you look at V transpose X, then I have V1 transpose, V2 transpose X, and I have V1 transpose X on the top, V2 transpose X at the bottom, right? And what I know is the number on the top, V1 transpose X. If I knew the numbers at the bottom, I would recover X fully, right? Because then I can, if I know the numbers at the bottom, right, then I can recover X is equal to, right? I can write down this expression, right? X is identity times X. So I get X equal to V transpose X, which I can then split as V1, V2, V1 transpose, V2 transpose X, right? It's just a trivial thing, but it's sometimes not apparent. Okay, let's write it all out. If I write like this, then I get V1, V2, V1 transpose X, V2 transpose X, right? If I knew the numbers here and the numbers here, then I can multiply this. It will look like this, V1 times V1 transpose X plus V2 times V2 transpose X. Right, so now we can interpret these numbers. So these numbers, so just visualize a little bit more. We just draw the shapes of all those matrices, so we're not missing how many numbers are there in each side, right? So we are, so put these 2 side by side, I get a square matrix. So they're both individually skinny, and then a small column V2 transpose X. The number of numbers here and here are different. One has R, one has N minus R in this case. But that's the shape that we're looking at. Okay, so we're asking what's the meaning of these numbers that are sitting in there. Right, and this tells you what the meaning is. It's telling you that these numbers are the coefficients of expansion in the V basis. Right, so in particular, for example, if I drop a perpendicular down like that, then you see that if I drop a perpendicular down here, but this is not mathematics now, okay? We're back to our intuition now. If I did drop a perpendicular down, we know that the foot will be inside range space of V1, and this will be perpendicular to range space of V1, so it must be in this space. Right? So therefore, we will expect that this can be written as linear combination of the columns of V1 and this vector, which is pointing up like that. Right? You move its tail to the origin, it's lying in range space of V2. So we write it as an expansion range space of V2. So we should be able to write this guy as V1 times Z, and we should be able to write this guy as V2 times Y. Right? By just that geometrical argument. It's not mathematics, right? But that's what we expect from the diagram. So what this algebra is telling you is, yes, all that is trivially true. I knew that already. I can tell you what Z and Y are. Right? It's telling you Z must be V1 transpose X, and Y must be V2 transpose X. So this diagram is the same as this equation. X is equal to this guy. This is the thing. Okay? And people, especially in the infinite-dimensional setting, especially in Hilbert space setting, engineers love Hilbert space because that's the first infinite-dimensional subspace of R infinity where actually all of Euclidean stuff holds true. So Cauchy-Schwarz holds true, true norm of A holds true, Frobenius norm of A doesn't make much sense, whatever the use is there. Right? You can almost make sense of inner products and things like that. You don't have metric associativity still, but most of the notions that we're using continue to hold in Hilbert space. It's the easiest one to work with, so very beloved of engineers. But of course, when you go up there, you lose matrices, right? I mean, all the other SPD and stuff become harder. It's not associative. You can't just move matrices around. So the abstract approach becomes important when you go to infinite dimensional spaces, right? So for example, you cannot put parentheses like this anymore. You can't move them around, right? For example, when I started off here, the parenthesis was like this, right? That was the actual parenthesis. Somehow magically it ended up over here and here. That's not allowed because multiplication is not associated with infinite dimensional spaces. Right, so everything is hard in infinite dimensional spaces, but one could still hope that something like this holds true. Right? So the way they make that hold true is like this. They write the same equation like this instead. Put the parenthesis back on this side. Like this. Write it like this. Okay? So then these two matrices are given names. These are square matrices. So this is called the projection onto the range space of V1. And this is called the orthogonal projection onto the range space of V2. Okay? And if you come back to this diagram, you can get a meaning now. If I move the parenthesis back like that, you see that this point is the orthogonal projection of X onto the range space of V1. And if you drop a line like that, you get this, right? This is the same as that. And this point is the orthogonal projection onto the range space of V2 of X. Okay, of course, here when we define these matrices, we define them to an actual construction. I actually wrote down what these matrices are. It's V1 times V1 transpose, U1 times U1 transpose. V1 should be an orthonormal basis for this plane, and V2 should be an orthonormal basis for that. So that's how you write it. Right? But the question arises, if I pick another orthonormal basis, will my matrix change or not? Of course, if you stare at this, you'll see it doesn't change. But still, it's useful to give a definition that does not depend upon this computation. And there's another set of equations you can write down, okay? And you can take an axiomatic approach to this. And many of your downstream classes will get very annoyed with me if I don't mention it at least once. I'll mention it, okay? So an orthogonal projector is a matrix P that satisfies two equations. Okay, the first one is that what's called self-adjoint, okay? It must be a symmetric matrix. If you take its transpose, you should get it back, okay? You can check that V1 transpose satisfies that property. All right, and notice that this property does not talk anything about matrix multiplication. It just talks about transpose, so it's fairly safe. It generalizes very nicely. Okay, and the second property is the one that is a little bit more annoying. It says that if you apply the projection twice, nothing happens. Same as applying it once. Okay, so we say it's an idempotent operator. Okay, so if you apply it, say, you can see from the diagram, that's what you expect. If I project it once, I come here. If I project it again, I stay over there. Right? It's very easy to check. If I take V1 transpose and V1 transpose, you get back V1 transpose because V1 transpose V1 is the identity operator. Right? So because of that, you get it back. Right? And it's with a little bit of elbow grease, you can show that if this is true, then you can write P as some V transpose such that V transpose V is the identity. Okay, that we can come back to this, which is where we came from. Again, you should all try to do it, okay, because in your downstream classes, they prefer this abstract approach. I don't know why, but that's how it is done in this community, okay? They'll talk about orthogonal processes and orthogonal information and things like that, and they'll use orthogonal projectors all the time, that word. So you should make sure that you can go between the two ways of naming things, right? So now also this brings us to a very important thing, though. Remember that if all the columns of V1 are orthogonal to each other, then V1 transpose V1 is identity, but V1 can still be a skinny matrix, right? So naturally the question arises, what is V1 transpose? It's mostly not the identity, but what is it? Well, it's almost the identity, right? Because identity, you see, satisfies this condition. Identity is its own transpose, identity is quite clearly identity. So an identity is an orthogonal projector, but not every matrix of form, not every orthogonal projector is identity. So for example, this matrix is not the identity, but it's the orthogonal projector of the range space. All right, so you have to get used to this kind of thinking about this, but it makes it very clear that these two are not the same, right? Not even for one column, right? So these two, this is a number and this is a big matrix, but it has some meaning associated with it. Okay, so these are the orthogonal projectors. Okay, there are oblique projectors too. So here, notice that we came in perpendicularly down, so then it's called orthogonal projector because this angle is 90 degrees. By which, algebraically, what we mean is we take the inner product between this guy and this guy, it will be 0. Okay, there's no like hidden expression over here, right? If I say something is an orthogonal projector, then Px, inner product, whatever is left over, will be perpendicular to each other. Right? So it's easy to check from those expressions over there that this is actually true. You can also have what are called oblique projectors. So when we did Gauss elimination, we were not doing orthogonal projectors. We were doing what are called oblique projectors. Again, I never mention these abstract terms because it doesn't really help when you can actually do the calculation. But you see that rather than going straight down, I can also take an oblique path like that down into the range space. Right? And if you think about it, this is also a projector in the sense that, let me take an arbitrary matrix now. Okay, so you walk by and you give me some columns, say A1 and A2 that lie in this space, right? A1 and A2, right? And then you give me, I pick a plane like this parallel to this, and you give me some columns over here, say A3 and A4, such that this matrix A1, A2, A3, A4 is square and invertible. Okay? I'm just giving some linearly independent columns, and I give you enough of them, such that the first two columns lie here, and the remaining two columns form an angle like that with the plane. Right? But they still intersect only at the origin because they're linearly independent. You can verify this too. All right, so these two subspaces are now complements of each other. Okay, but yet one is tilted and has this one 90 degrees. Right? If I now form a projector based on these two matrices on the first two columns, I'll get what's called an oblique projector. For an oblique projector, the range space is still given by A1, A2, but the guy on the right is not. I'll give you the pleasure of writing it down yourself, but it only satisfies this property, but P is not equal to P transpose anymore. Only for orthogonal projectors do you have the symmetry condition. For oblique projectors, the idempotency slopes, right? If you come in like that, you land here. If I go in like that again, I still stay over there, right? This line is drawn parallel to the orthogonal, to the complementary subspace that you picked, which is A3 and A4. Determine this angle that you're going to draw. Okay, when we did Gauss elimination, we were doing oblique projections, right? So if you really want to understand what an oblique projection is, you should actually work all of this stuff out. Write down an oblique projector, look at it, make sure that if necessary, you can eyeball one and write down one that doesn't satisfy this condition but satisfies that condition. Okay, it's very trivial to write down. I'll leave it to you to figure it out. It's that XY transpose business that I was doing. Okay, that was an oblique projector. Okay, so think about it, right, and fiddle with it until you produce an actual oblique projector out of it. All right, so that's orthogonal projectors, oblique projectors. We understand what this expression over here means. So let's go back to where we stopped. So when we're doing this, when we're solving the equation by SVD, right, we started with, let me write it down again. So we started with AX equal to B. We did some calculations. We ended up with V1 transpose X is equal to sigma R inverse U1 transpose B, right? And we said, how do I go back to X if I just know V1 transpose X, and now we know the answer, right? So we know that we can write X as V1 transpose X plus V2 transpose X. And we know that these numbers are independent of those numbers. Right? We know that now from that expression over there. So we know that X can be written as V1 sigma R inverse U1 transpose B plus V2 times whatever you want to call these numbers, Y2, for example. Right? So this is a shortcut way of writing it down. It doesn't have much geometrical meaning of why this particular one, but it would be still very natural to write this expression down. Right? And this part is called the pseudo-inverse. Right? And you can just say, well, Y2 is free, so why not just pick it to 0, because I can pick it to be anything. Right? I mean, you don't say minimum norm or anything like that. It's another way to think about it. Now, let's go back to this picture and then this projectors, and we give one final way of thinking about pseudo-inverses. Right? And the last one is important because I will look inside that formula that I wrote down over there now. So let's go back to the geometrical picture that we drew of the action of A using the SVD, right? So we have U1, U2, sigma R 0, 0, 0, V1, V2 transpose. Okay, so A is a map from, say, Rn to Rm. We go this way, Rn, we end up with Rm, let's say. Then we know there's a row space on this side, row space of A. And then perpendicular to that is going to be the null space of A, right? This is the same as the range space of V1, and this is the same as the range space of V2, right? That's why we know they're perpendicular to each other, because all the columns of V1 are perpendicular to the columns of V2. And on this side, we have a similar picture. We have another hyperplane that's exactly the same dimensionality as the range space, as the row space of A, right? Those two ranks are the same. Column rank and row rank are always the same. So range space of A, it's got a 0 somewhere. This is the same as the range space of U1, and then it's got a perpendicular space to it. This is the left null space of A, which is the same as the range space. And these two spaces are perpendicular to each other because the columns of U2 are perpendicular to the columns of U1. Right, so we have a complete pictorial diagram of how this matrix A acts. But in fact, we know a lot more. We know also how a circle here is mapped to an ellipse over there. Right? We know exactly the shape of the ellipse, where it's oriented, and things like that. Okay, using the columns of U and the columns of V. Okay, so we have a complete understanding now of the map A. Right? It's very, very obvious. It sits with simple. It is simply related to the numbers in the SVD. That is an early factorization that was not quite true. Okay. So now we're saying, okay, I've given you some column B, right? Ax equal to B, so give you a column B. And I want you to find an X that maps to B over there. So the process we are following for solving the solution is very simple. We're saying, first, find the smallest change that you can make to B. So I'm going to add a vector R to B, which is called the residual. You're going to do the least possible damage to B, such that it actually comes into the range space. Right? It should come into the range space. Now, after all this talk, we know exactly how to do that. If you had to do this abstractly, you say, well, take the orthogonal projector under the range space of A and apply it to B. That's what we would do. Right? Of course, we know an exact expression for that is U1 transpose times B, right? Because we have a basis for the range space of A, which is U1 transpose. So I want to know R. I know what that one is too. I can just apply the orthogonal projector for projection onto the null space, the left null space of A on B. Okay, so now you see why the left null space is important. It looks like it should have no bearing on the problem, but yet it also gives you the right thing to do. It tells you how to compute R, right? So both of these can be computed. This is of course just U1 transpose B, and this is of course just U2 transpose B. Right, but I can be very, very abstract and say, oh, use orthogonal projector into range space, okay, to bring B into the column space with the least possible damage in the two norm sets. Right, so now once this guy is here, then I know there are many x's that map to that point. Right? If I take an x like this, I can find an x that goes over there. But how do I find that x? Well, there are two ways to do it, right? One is, notice that if I don't look for an x outside, but I only look for an x in this plane over here, I just have to find an x in the range space, row space that maps to B, that's very easy to do. Why? Because inside this plane, the action of A is very, very trivial, right? Because A acting on V1 is U1 sigma 1 like that. A acting on V2 is U2 sigma 2 like that. A acting on VR is sigma R UR. So if I can expand B as a linear combination of these, I can take a linear combination of these to get the correct X. The same linear combination. Right? For example, if B was, let's say B was U1 sigma 1 plus U2 sigma 2, then I know that X should be V1 plus V2. Right? Because I multiply this by A, I multiply both of these by A, which will give me this and this. Right? So it's very trivial to go backward if I know how to expand B in terms of U. That's easy to do. We just wrote it out, right? So I know exactly how to expand B in terms of U. B, right? This is already inside the column space, right? And so we already have the expansion of projection range space B in terms of U1, right? If I write this out in great detail, it looks like this U1 transpose B, plus little U2 transpose B, plus little U3 transpose B like that, up to little UR transpose B, right? If I write this out in outer product form, it looks like that. So I know exactly the components of the projection of B into range space for each of the little, for each of the columns in this basis set of capital U1, little U1, little U2, little U3, up to little UR. I know exactly the coefficients that have to be there, right? It's just the corresponding products. Right? So it's very, very trivial to expand B into this orthonormal basis, which is using the fact U transpose this identity, okay? So we did that already, so that's what it is. So since I know how B can be written in terms of U1, when I apply A inverse, I just have to apply A inverse to each of these guys individually. Right? It's a linear thing, so I can apply to each one individually. If I apply to each one individually, I know how it goes, right? What does U1 go back to? Let's look at this, right? U1 gets mapped to V1 divided by sigma 1. U2 gets mapped to V2 divided by sigma 2. UR gets mapped to VR divided by sigma R, right? That will be the back map. Right? It's 1 to 1 onto that, in that space, right? In this space, mapping is sort of unique, so we can figure it out. So we guess that our X should look like this. Replace U1 by V1 and replace U1 transpose B divided by this one, like that. Right? Similarly, this map, U2 gets mapped to V2, and this coefficient should get divided by sigma 2, right? Because it's a linear map. If I multiply the right-hand side by 10, if I multiply this side by 10, I should multiply this side by 10. Right? So if this is U1 transpose B, then the U1 transpose B should apply here too. If this is multiplied by 20, I should multiply this side by 20 to keep the equality going. Right? So if this is U2 transpose B, then the U2 transpose B appears on this side. So that's what we are doing. You go all the way up to UR transpose B divided by sigma R. Right? Now I put this all back together and see what I get, right? If I factor it out, I put the V1s back inside their matrix. Then I put sigma 1s, 1 over sigma 1, 1 over sigma 2 in a column. And I put all this in a column, U1 transpose B, U2 transpose B, and so on. I get the expression on the top. But that is exactly V1 sigma R inverse U1 transpose B. That's exactly what we computed before. Right? But now I've taken it all apart and done it component by component, okay? So I know exactly how the V1 through V2 here, so V1, V2 are mapped onto this semi-major axis, semi-minor axis, and so on. So it's easily able to map it back, right? So the way we say it is that if I had used V1 through V2, V2R, V1, V2, V2, V3, and so on as the graph paper on this side, if I had used U1, U2, U3, U4 as the graph paper on that side, then the matrix A is the matrix sigma R. Right? We say in this new basis, the matrix A is the matrix sigma R actually. We've restricted A to this space, and it becomes a square invertible operator sigma R. Right? This is the abstract formulation of this problem. If I restrict A to its row space, if I restrict A to its column space on the right-hand side, and if I pick the right basis, then the matrix will appear as a diagonal matrix. And the inverse of a diagonal matrix is very trivial, right? We just invert the components, which is exactly what we did. Right? What are these two operators doing? They are doing the restrictions for us, right? U1 transpose B is what B would look like if I restricted B to lie inside this and then looked at its expansion. Those are the numbers that would go in. What is B1 times this doing? So if I block this off, these are the components of X. if restricted to this range, to this row space. But I want to write it as if it belongs to this big parent space, so I must inject it back, add more numbers to the column so that it goes back into this parent space. And V1 undoes the projection, okay? It embeds this column vector back into this larger space. Okay? It adds more numbers to it. Okay, the most trivial way, for example, would be if I have a column in this direction and it's length 2, I can think of this as a number 2, or I can think of it as a number 2, 0, because I'm thinking of it as a column in this bigger space. All right, so I can write this as my V times sigma R inverse U transpose V. Okay, that's what I sort of injected back in by using them as coefficients of the columns of V. Okay, so this is all the more abstract way of saying things, but of course, I hope graphically it's very obvious. Okay, so each component is pulled back onto and over here, and this X is the minimum norm least square solution, the one inside the row space. And that's where we stop with the pseudo-inverse. If you want to find all possible solutions, very trivial, right? You take the minimum least square solution and add anything from the null space. So you draw the affine subspace through this point. Right? What does anything here looks like? Any column here looks like V2 times Y2. Right? It's a linear combination of the basis for that space. So you take X and you add V2 times Y2 over here, and you get an arbitrary solution X in that space. Okay, so those are the two right-angled triangles we draw. This one and this one. Right? And if you look at this construction, it sounds intuitive that this pseudo-inverse is actually unique. Right? Because I can describe this projection without respect to the SPD at all. I can just say projection of the range space of A. And I can say that this construction is unique because the map from this hyperplane to this hyperplane is completely unique and well defined. So the pullback is unique, right? And then, of course, this is the part that I threw away, so that's fine. Right? Of course, this is just me waving my hands and saying it's unique. You should actually prove it's unique either by this approach, or there's another approach given by Roger Penrose, where he also showed it as unique, but he showed it this much more cute way. Okay, so I'm going to write it down, and I'm not going to say much more about it. Okay, so we know what A dagger is now, so it's a pseudo-inverse, but this is not how Penrose defined. Okay, so the Penrose pseudo-inverse is defined like this. So remember, when we first defined left inverse, right inverse, we defined them without the aid of a computation procedure, but as solutions of certain equations. We said anything is a left inverse if it satisfies this equation, anything is a right inverse if it satisfies this equation, and anything is an inverse if it satisfies a pair of equations, like that. Right? Those were the three definitions. Right? In these two cases, the solution is not unique. In this case, it may not exist, but if it does exist, it's unique. Okay, here too, it may not exist at all. Right. So that is the way we started the definition of inverse. So one could ask, is a similar definition of the pseudo-inverse, right? Rather than giving a big, elaborate, constructive definition, there's a short and sweet equational representation of the pseudo-inverse, and Penrose gave that. Okay, so it looks very, very funny, so I should write it down. Okay, so the pseudo-inverse is defined to be a unique matrix that satisfies 4 equations this time. Okay, the first one is this one. The second one is like this. The third one is, and the fourth one is this one. Okay, by using the SVD, you can prove that the way we define A dagger actually satisfies that equation. Okay, so you can use SVD to show that, well, okay, if I take this as a pseudo-inverse, plug it in, you can check left-hand side is equal to right-hand side. All of this. Okay, you can check that, and you should, of course, do it and make sure that it's true. Okay, what is the genius about this is that, remember, the SVD is not unique, right? So the genius of this is that Penrose showed, independent of the SVD, that there's only one solution of this. So remember, so the existence is not difficult, right? We showed the existence of such a matrix A dagger. The question is, are there more than one A daggers? And Roger Penrose showed, no, there isn't, that there's only one solution of the set of equation. Okay, what is the difficulty, right? You see the difficulty is that if these 3 equations are linear in A dagger, right? The numbers inside A dagger appear only once in each of these three equations, but this one is a nonlinear constraint on A dagger. So proving or analyzing the system of equations is not difficult. So you should try it. However, it is not easy either. Okay, so the fact that Penrose's name is attached to it means something is hard somewhere. So it turns out that it is not that simple to prove that the solution of the system of equations is unique, but you should try to take a whack at it. Okay, so we will not take this abstract approach. This abstract approach is useful when you go into some infinite dimensional spaces where you may not be able to directly access the SVD, so cannot prove SVD exists, so then you cannot go that way. But you might still be able to make sense of the lack of parentheses in this expression, and then still be able to force this to go through. Okay, now that is one reason why Penrose inverse is useful, but there's also a second reason why Penrose inverse is useful. Okay, and the second reason is that there are some applications where you cannot have all four constraints hold, and you don't need all four to hold. Okay, so you can drop one or the other of this. So when that happens, then people will call those inverses as like 1, 3, 4 Penrose inverse, 2, 3, 4, or 1, 2, 4, like that, depending on which one they happen to drop. So if you look at Karl Mayer's book, he gives examples of these kind of pseudo inverses, which are not the one that we wrote down, but which only solve a subset of these equations when solving differential equations. Okay, so I'll talk a little bit about it later on, but in my opinion, it's not very useful though. So I will not spend too much time about it, but it is there as a theoretical tool. Okay, of course, if you drop one of those equations, the pseudo-inverse is no longer unique. So if you drop any one of them, pseudo-inverse doesn't become unique. Okay, there are many solutions of that, so it's not that useful, but it's still sort of useful because it has this algebraic property still left over from it. Okay, so that's the pseudo-inverse. You can write down arbitrary solutions. For those two special cases, when A is full column rank and full row rank, cases A has full column rank. Remember in this case, sigma R 0 U V transpose equal to A, right? So there is no V2, U2, so the U is the same as U1. Sorry, there's no V2. Okay, so the row space is all of this part on the left. So that's of course a special case. This is what's normally called the least squares problem, and in this case you can do it by a QR factorization. So you can do this instead by, you can form the least square solution by doing QR. The Q is orthogonal and R is upper triangular, so Q transpose Q is identity, and R is upper triangular 0, like that. Okay, and this is called the Gram-Schmidt process. We've all done it before. The proof is just one left-hand side of the singular variety decomposition. Okay, so I will not talk about it. If you can do the SVD, you can trivially do this in 2 lines. Okay, so you should of course try to prove it. If A has full row rank, right, and this decomposition can be computed by hand, you can show it's equivalent to doing the LU factorization of A transpose A. Okay, so that's actually called Gram-Schmidt too. So A is if A is full row rank instead, then A can be written as U sigma R 0 V transpose. This time there is no U2, so the range space is all of the right-hand side. There's no projection to be worried about. You can actually solve the equation exactly. Right, in this case, you can just compute LQ factorization of the matrix instead, which is the same as the QR factorization of A transpose. So it's Gram-Schmidt of the rows of the matrix A, and from that, you can do it very easily too. Okay, so again, the reason why this L is good enough is because it's lower triangle is 0 Q. Because you see, it's like taking the U into sigma R. Okay, so that's sort of like what's going on. You really don't need U and sigma R of that. Okay, you just need that part to be invertible. We can get that with the LQ factorization. Now, those two factorizations are about 10 times faster than the SVD. So in practical calculations, those are the two factors that I actually use, not the SVD. Either you will do the QR factorization or the LQ factorization. Okay, for a while in MATLAB and Python and stuff, they would not expose the LQ factorization that's there in LIPAC. I think in Julia that is still the problem, I think. They only have the QR factorization exposed, so you have to go, take compute the QR factorization A prime to get the LQ factorization. It's a small headache, but in LIPAC, there actually are QR, LQ, and all of that is over there, and you can easily get it from that. So you can do you only reach for the SVD if you think something is going wrong. Okay, so I should say something about it now before we go on. So let me just write down a little bit. So the SPD is nice theoretically, and we saw it as nice properties, and you prove a lot more properties about SPD in the exercises. But computationally, it's a useless tool, okay, pretty much. You should never compute SPD unless you really have a good reason. QR and LQ are the ones that you should do. At least in Julia and Octave, if you do A\B, it'll automatically compute either the minimum norm if A is fat, or the least square solution if A is skinny. Okay, what happens if A is not full rank? Well, if A is full rank, the code cannot detect it usually. Okay, it'll just go with the size of the matrix. Okay, but something will actually go wrong, of course, in real life, right? So what will go wrong? So if the code is always doing LQ or QR and not doing SV ever, what can go wrong? So what will normally go wrong is that some number that should have been 0 will come out as a tiny number, right? So when you do LU factorization, for example, we compute singular values, we expect it to get sigma 1 up to sigma r and then a bunch of zeros. But when you're doing when you're doing SPD in the computer, you're making small errors, and these zeros are the result of exact cancellation between sums of numbers. And because of the little jiggling that you're doing in the floating point arithmetic, these zeros will not become out to be exact zeros, but they'll come out to be something which is close to missing position. Okay, so roughly these numbers in 14-digit arithmetic will be roughly 10 power minus 14 times that n size. Okay, that's how you know that those are probably in trouble. In real life, of course, you cannot maintain full precision. It's too expensive to do it that way. So the software takes a little bit more liberties to go fast. So there'll be an extra factor of roughly n, where n is the size of the matrix in front of it. Okay, so if you have 1,000 by 1,000 matrix, you will lose, in addition to, you're just doing arithmetic in 14 digits. In addition to those 14 digits, you lose about another 3 digits. Right, so you'll be roughly about 11 digits of accuracy. If you're working in a million by million matrix, you will lose an additional 6 digits in the smallest singular values, okay? So you'll be careful about what you call a 0 or non-zero and floating point. It depends upon the number of computations you had to do to get to that point. Say, for example, we're doing calculations in single precision, right? If I'm doing calculation in single precision, roughly I'm carrying about 7 digits at most. Right? And if I have a 10 million by 10 million matrix to do, then you probably are getting all garbage at the end of the day. Even numbers the size of O of 1 comparable to sigma 1 are probably zeros somewhere. Okay, why am I saying probably? Actually, even though I wrote the polynomial as n over here, formally in the calculation, if you do the actual computation, actual error analysis, the actual number that appears here is n cubed. That's the worst case error analysis. Okay, so we're saying if all the floating point errors that I'm making in the code go against me, how big will the smallest singular value come out to be? So people have done this calculation. It's very tedious, very boring. I used to teach it in this class. I don't teach it anymore. Right? It's n cubed over here. So think about that, right? If my matrix is 100 by 100, right, this number is already 10 power 6. Right? That means I barely get 1 digit of accuracy in my single position calculation. Remember, all your GPUs, you want to run in single position because it's takes less space, it runs faster, right? It's so much safer. But there's a price you pay for this, right? Because the very fact that you're using a GPU means you're doing billions of calculations, right? Otherwise, what's the point? Right? So that number of calculations basically is what's appearing over here in the calculation, right? So that number is going to work against this number. Right? So that's why doing things in the GPU is so fishy in the first place, right? Because you're doing a billion operation, but you're only carrying 7 digits of arithmetic. So pretty much you're replaced by a random set of numbers. You'd be okay too, right? So you have to be a little bit careful about this. Why it is not always the worst case is that sometimes the floating point errors hurt you, sometimes they help you, right? Sort of like a random walk in some sense, right? So if you take that approach that floating point errors are random, and if you open Nick Heim's book, it gives you a graph of floating point errors which shows conclusively that it is not random. Okay, IEEE floating point arithmetic is very, very, very far from random as you can be. It follows a very strict pattern. But still, let's say we all like statistics and say, oh, it's a drunken man walking around, then you would put a square root around it, right? Law of large numbers will say roughly you should take a square root of this. You don't, when a drunk is walking, he drifts from the audience roughly at the rate of square root of the number of steps he takes. So that's called the random walk. So you normally would take roughly a square, which drops you down to about 3 over 2. That's roughly a better estimate. But in the code, they do something better than this. Okay, so usually, in my experience, it doesn't go even as bad as this. It goes roughly like linear usually. So you get more than you think. So that's why single position is reasonably safe. If you drop to half precision, of course, things get much worse, right? If you drop to 4 digits of arithmetic, You can get half precision machines too. Then you'd be really, really careful. And this is always floating point arithmetic. Now, some of you, at least in the old days, in fact, about 10 years ago, when I first had a cell phone, the cell phones did not have floating point arithmetic units because they're very expensive to build and they're very power hungry. So people had fixed point units, right? So fixed point units are still nice because in a fixed point unit, the hardware is much simpler than a floating point unit. You don't have to worry about the exponent at all. So fixed point unit means, you fix your point, like you say, I'm only going to look at numbers from 1.7356 like that, okay? So you don't use this number, but you assume that everything is, all the numbers you store are after the decimal place. In floating point, you say, I also store the exponent, like say 32, something like that, okay? So you store those also. So in fixed point units, you don't track the exponent. The exponent is always assumed to be 1, so 10 power 1 in this case. And you only keep these bits over here. So you lose digits faster if you're not careful in a fixed point implementation than in a floating point implementation. So these things don't hold true in fixed point implementation. When you're working with fixed point implementation, you have to be super careful about what you do. Okay, when you're working in fixed point units, you must make sure that all the numbers you produce are very, very close to 1. If you say if you fix a digit over here, then you must make sure that all subsequent calculations tend to have some number in this part. If they start going like this, right, and the machine truncates over there, you will set this number to 0 straight away. Right, so fixed point is even more finicky than floating point. But if you know what you're doing, and you're using a good algorithm like something in LIPAC, you should be able to get a fixed point arithmetic algorithm to mimic a floating point algorithm. Should be no difference almost. Okay, but you must choose your scaling correctly, and you must set your fixed point correctly too. When those two are done, then this will work, and everything I said about floating point errors will continue to be true. Okay, so we're going to make floating point errors, right? So what happens when I actually invert this many, right? If I compute the pseudo-inverse, I should have only inverted this part. But when I give it to MATLAB to do, it's going to invert the whole thing. Think, oh, this whole thing is sigma r now, right? Because I did not see any zero eigenvalues, zero singular values. It'll invert the whole thing. Of course, if I invert the whole thing rather than just sigma r inverse, I do have sigma r inverse over there, but I have all these 1 over epsilons running around too, like that, right? So what happens normally is that, let's say that to be able to talk about digits correctly, we first normalize my solution before I start. Okay, so I start with ax equal to b, right? I first normalize this, right? A good way to normalize this set of numbers is to first divide by the largest entry in A, okay? So that you say that, well, okay, right? If I divide both sides by the same number, I don't change my solution axis, right? It's a linear system. So I scale everything so that my largest number in A is 1. Right, so roughly in your head you're thinking sigma 1 is roughly 1, okay? It could be off by some polynomial in n, but that's a good mental place to hold, okay? So when I say 1, that's a large number for you. Anything above 1 is 1 is a normal number for you. Anything above 1 is large. Anything below 1 in magnitude is small, okay? That's how we're going to talk about it now, because we've normalized one set of numbers somewhere in this equation. In this particular case, I picked A. Right, so sigma 1 is roughly 1, okay, at least some polynomial in n, but we'll be cavalier about that. So we expect that the smallest number that I can meaningfully compute, the smallest singular that I can meaningfully compute will be, say, in 14-digit arithmetic, about 10 power minus 14 times 1 times n, for example, n is the size, right? Anything below that is really a 0 for me. So how do I detect this, right? Because I don't want to compute the SVD. Well, we notice that if I compute the norm of A, then we know it is the largest singular value in A, right? Because u sigma v transpose, you drop the u and the v. So you take the norm of u sigma v transpose, that is the norm of sigma, and that's the largest entry in sigma, right? Because sigma is a diagonal matrix. We proved all of that, okay? Right? We know it's roughly 1, so we don't need to compute it. Now, what about norm of A inverse? If A was invertible, let's say it's a square matrix, keep our life simple. Then if I take the inverse of this, right, I take inverse of this, this, and this, the v will be something like that in the square case, right? Again, I can drop v and u and get norm of sigma inverse. Right? It is the 1 over the smallest singular value instead. All right, right? So we have a meaning for the largest singular value of the matrix and the smallest singular value of the matrix, right? So now you see what they call singular values. If a matrix A is not invertible, we say it's a singular matrix. So a singular matrix is flagged by the fact that the smallest singular value actually goes to 0. Okay, so it's called the singular value of the matrix A. All right. So we know that if 1 over sigma min is large, then you're going to meet trouble, but you don't want to compute sigma min, right? What you see that what we really care about, if you ignore the scaling then, is this product. Okay, and there's a more detailed calculation in the note, which I will ask you to do eventually. So this product is the one that is scale invariant. Sigma max over sigma min. The largest singular value divided by smallest singular value is invariant to the scaling of the matrix A. And we can show that this number is what will determine something, okay? So we're going to come to that. So this number is always bigger than 1, right? Because the largest singular divided by the smallest one, so the smallest is going to be is 1. And if this number is large, then you're going to be in trouble because in the homework, you'll be asked to prove this expression. Okay, we can show this. So we have, let's say that you're trying to solve ax equal to b, right? When you did the floating point calculation, you're going to compute some x hat. Whether you're doing minimum norm, whatever, you're going to compute something else, let's call it x hat. And that will not be equal to b, but it'll have some error in it. Right, we just call it residual. Right, it could be conscious like in a least squares problem, it could be just, it's a cumulative effect of rounding errors, least squares errors, all kinds of stuff, but it is there. So normally what people do is, in the beginning they used to write the R over here, which is very confusing. What we do instead is we write it as E instead, and I think you already did that. So this is called the backward error, okay? We say that, instead of writing the R, you can write it as an E instead, okay? You put the perturbation in the matrix A, right? And we're saying that the computer solution is the solution of a nearby problem. Now what the LAPACK routines guarantee to you is that the software is written in such a way that this E that they produce with a floating point arithmetic, okay, will be smaller than some polynomial in n, let's say 3 over 2, but it's actually a little bit bigger, times the machine position. So if you're doing 14 digits arithmetic, it's going to be roughly that much. Okay, so what the software is actually guaranteeing to you that the computer solution that they're returning is the exact solution of a very, very, very close by problem. Right? By close by, they mean that you must sacrifice some digits in the matrix A. You're going to change some digits, some of the entries in the matrix A, but you will guarantee that you will not touch any digit that is closer than this. Okay, so if n is equal to 1, you will not touch any digit in the first 14 leading places with respect to the largest number in the matrix A, not individually. Right? So for example, if the matrix A looks like this, 1, 0, 0, 0, then I might add a 10 power minus 14 here, but I can also add a 10 power minus 14 here, right? This one is wrong in all digits, but still the total error you're making in the absolute sense is still holding 14 digits. Okay, so we will perturb everything after the 14 digits, and then after the slight perturbation, the computer solution will be an exact solution. Okay, that's what MATLAB guarantees to you. It doesn't guarantee that the computer solution is close to the original solution. So one could ask, how far is the computer solution from the actual solution? Right? Unfortunately, this is not good news. Okay, it turns out that this is roughly, if you look at the relative error, so you take out the scaling in x, then this is roughly 10 power minus 14 times n power 3 halves times this number that we have over here, sigma max over sigma min. Okay, so now let's think about it. If this number is 10 power 14, then these two numbers cancel, and the upper bound is bigger than 1. Right? So the bigger the condition, and the condition doesn't depend on the size of your matrix. Right? You can have a small matrix with a large condition number. You can have a huge matrix with a tiny condition number. Right? This is a completely separate calculation that you have to do. So unless you know this number, you have no idea how accurate the computer solution is. Okay, you'll be very, very careful about this. This is true for Ax equal to B. It is true for Maxwell's equation. It's true when you do Laplace transform. It's true for every linear operator. It's true for every nonlinear operator. Just because the residual is small, if you put this R back like that, this could be small. It just tells nothing about the error in your solution. Okay? In the case of LAPACK alone, you have to convert that R to an E. Remember, 2 norm of E is roughly 2 norm of R divided by 2 norm of A, 2 norm of B, I think. You have to normalize it, get the E. You then put the E back here. Okay, so you have to put it back like this. And you must compute this expression over here. Okay, that's how you have to do it. This is called perturbation theory. Alright, so if the condition number is large, the solution is going to be wrong. It could be wrong for various reasons. It could be that you set a small zero singular value to back to non-zero. You should have at least treated that as 0. It could be it could be that it had 0 small singular value just because that's what it was there in the first place. It could be floating point errors, whatever. All of those errors are lumped into this expression over here. So what the software will do at least MATLAB, is that it will monitor this number, it will compute a surrogate for this number. Okay, so remember this number is roughly norm of A times norm of A inverse. So it will do a statistical estimate of these numbers, okay? And it will warn you when this number is too large. So if this number becomes roughly 10 power 6, I think it starts warning you. I'm not sure what the warning limit is in MATLAB, but it'll warn you. But if you're using LIPAC, then there are routines to compute this number without actually doing the full SVD, so they're pretty fast. You just need the LU factorization, you can compute an estimate of this number, a statistical estimate of these two numbers, and you can get this number, and if this number is large, you're in trouble. Okay, for most calculations, so you get paid money, that's the way I would put it. Okay, so so physics systems have tend to have like telescopes and radar systems. Those numbers will go like 10 power 22, 10 power 24. It'll easily exceed your mission position. Okay, of course, when that happens, you can still compute AX equal to B, but require special techniques to do it. Okay, for example, when you go to, if you've ever seen an ultrasound, it looks like horrible. And the reason for that is that they have to solve the equation AX equal to B inside it. And you can prove mathematically that if you took the full infinite matrix for an ultrasound system, this number would be infinite. So when that happens, there's a name for it. These systems are called ill-post. That means the condition number is actually infinity. If this condition number is large but finite, then we say ill-conditioned instead. Okay, and it's just a fact of life. Whenever there's a high gain path in your system, your system will be either ill-post or ill-conditioned. That's just the way it is. Okay, the more amplification you have somewhere along your path, it will be natural to expect this to happen. Right? It's just part and parcel of this game, and that's the number you should watch out for. And in MATLAB, it will warn you, but for the other ones, you got to issue a warning yourself. Okay, and the important thing is, remember the residual can be small, but it doesn't mean anything. Okay, so I just write that out. So if you look at just the error in some norm, this is called relative residual. This number is not good enough to tell whether your solution is accurate. Okay, I'm going to repeat this 5 times in this class because I've been to many theses in engineering where people are solving fluid dynamics, Maxwell's equations, elasticity equation, and they report this number as being small. And it's not even small to have a chance of being accurate. Okay, so they will report numbers like, say, 10 power minus 3. Okay, by now you should be convinced that 10 power minus 3 is nowhere close to giving you 1 digit of accuracy in your solution. Right? Many people use, for example, iterative methods to solve equations, and they'll stop with 3 digits. You can stop. I cannot stop you from doing that, but you cannot claim then that you have computed the solution even to 1 digit of accuracy, right? Because the condition will probably be much bigger than 1,000 for sure. Right? The condition will go to multiply whatever number you pick over here. If this number 10 power minus 3 and the condition was 10 power 3, then basically you're talking about junk in your solution. They plot the solution and say, oh, it looks like a solution. Of course, it looks like, and I think that's two opposite ends of the world. So, right? So you have to be careful, okay? So when you cannot look at the residual and claim you're something about the accuracy of the solution, that's a separate calculus. Find the condition number 2. All right? All right, so in the next class, we're going to go on to infinite dimensional systems. So you should start looking up spectral theory. And we'll start with difference equations. So some of you have never seen a difference equation before, only a differential equation. Difference equation. But these are significantly easier. So what I'm going to do is I'm going to post my notes from my undergraduate class on the website. So please download that and look at it. It's very, very different from what most engineers have learned about difference equations, okay? That's not the way I teach it. Many electricians have done it, but it's completely wrong what you learn, so you should read the way I do it. Okay.